Okay, our final topic in our introduction to the limit equilibrium method is the general method of slices. And the method of slices, we're going to look at a general method, but in our next sequence of videos, we're going to look at a number of more advanced methods of slices. And so the way this works is, as shown on the right, you take your failure surface, and instead of treating it as a single sliding mass, you break it up into a series of slices with these vertical dividing lines between the slices. And then this shows 1, 2, 3, 4, 5, 6. You could have 10, 15, 20 slices. The more slices you have, the more accurate the solution. At some point you get a point of diminishing returns, but it's kind of like when we solve the finite difference method or the finite element method, where you subdivide the problem domain into cells and nodes. But in this case, the most convenient way to analyze this is a series of slices. Sometimes you use a wedge analysis where you have an active wedge, a central block, and a passive wedge. This would have 3 slices. And this is a general non-circular case where you just break it up into any number of slices. And so in the general case on the left, you have each of these individual slices. You can do a free body diagram where you have the weight of the slice acting through the center of the slice. At the base of the slice, you have a normal force and a shear force. That shear force is based on the mobilized shear strength acting along the base of the slice, along the sliding surface. And then on the sides, you have normal forces, which are E, I, and EI plus 1, assuming we're counting from right to left. And then we have vertical side forces, xi and xi plus 1. And so we end up doing a free body diagram. Based on this formulation, you can come up with an equation for the factor of safety, where you add up the moments and sometimes some forces based on these individual slices, and then you put that all together and you get an overall factor of safety. And so with the generalized method of slices, this is the way we often set it up. Assuming we have a circular surface with a radius r, again, the red dot is the center of the circle. If we're looking at this slice here, then we have a moment arm AI. The subscript I indicates that we have to do this for each of the slices. WI is the weight of the individual slice. And then we also need to know what the angle is along the base of the slice. So right at the center of that base, what is the angle? And we call that alpha. And that we have a sign convention. If we're looking back, if it slopes up towards the head of the slope, that's a positive angle. And on the toe of the slope where it's going this way, this would be a negative angle. So you can see what it would be on either side here. Now, using that sign convention, we can calculate the moment arm AI. So this distance AI, by the way, this angle right here between this line coming down from R and W, that's also alpha I. And so this moment arm AI is is R times the sine of alpha, okay? And so that's this individual AI moment arm is R sine alpha. So the driving moment, let me back up. So the driving moment, if you apply Wi times alpha I for each one of these slices and add that all up. And by the way, if you're on the right side of this center, the weight of these will be driving failure, and if you're on the left side, it'll be resisting failure. But those all add up, and you get the driving moment now is a summation. It's R times Wi sine alpha I. Now the resisting moment is is you look at the shear force along the bottom of each of these slices, and you have to add that up and multiply it by its moment arm, which is r. And so we have the sum of r times SI. R is the radius, and SI is the individual shear force. That shear force is the shear stress times delta Li. So delta Li is the length along each individual base. And these can all have the same width, but they'll have different length. For example, this one would have a long length, and down here you get a pretty short length. So you have to calculate that separately for each one of those. And so, and that shear stress tau I is equal to the individual shear stress SI divided by the factor of safety. It's like where S equals C plus sigma tan phi. So it's like the tau I is the mobilized shear resistance, and so we replace that with SI over F. And now we can say the driving moments are equal to the resisting moments, and we set this term here equal to this term down here. And we get this equation, and we can divide both sides by R, and we get the sum of W sine alpha is equal to the sum of SI or delta Li divided by F. Solve that equation for F, and we get the factor of safety equals the sum of SI times delta Li divided by the sum of Wi times sine alpha I, which again is just this. These are the sum of the moments resisting failure divided by the sum of the moments driving failure. And if you plug in the C plus sigma tan phi for SI, you get this. So this is the general equation for the general method of slices. Furthermore, if phi is equal to 0, then this term goes away, and we're left with F is equal to the sum of C delta Li divided by the sum of Wi sine I. This is sometimes called the Swedish method. The Swedish method of slices, because if you compare it back to the general Swedish circle equation, which was based on a single sliding mass without slices, notice the similarity. The cohesion times L, the length of the sliding, the failure surface times the radius, and so now we have C times delta L, which is the length at the bottom of each slice times the cohesion along that slice, and we add all those up. And then down here we have the overall weight times the moment arm to the center of mass. And here we have Wi times sine alpha I. This sine alpha I is kind of helps give it the correct moment. And so these are very similar. This is just, once you divide it into slices, that's what the factor of safety looks like. So we're going to do an exercise for our homework using this Swedish method of slices using this equation here in the middle.